Let me ask you something. What is the most rebellious substance in the universe? What is the one material that looks at the laws of physics, the nice, clean rules that everything else follows, and says, no, I don't think I will. You might guess something exotic, some rare element forged in the heart of a dying star, some bizarre plasma, some strange quark matter from the edge of known physics. But no, the answer is sitting in a glass on your kitchen table right now. It's water. Plain. Ordinary. Water. And I want to tell you something that genuinely unsettles me. The more I have studied water, the more disturbed I've become. Because water doesn't just bend the rules a little, it shatters them. It does things that by every reasonable expectation of chemistry and physics, it simply should not be able to do. And the fact that it does these impossible things every single day, in every glass, in every ocean, in every cell of your body, is the only reason you and I are here to talk about it. So here's what I want you to walk away with today. I want you to see that water is the strangest liquid on this planet. That its weirdness is not some minor footnote buried in a chemistry textbook. Its weirdness is the very foundation of life itself. And I want you to understand why. Because when you dig into the physics, the real physics, the explanation is beautiful, genuinely beautiful, but also deeply unsettling. Because it means the entire universe is balanced on a knife's edge. A knife's edge made of something called a hydrogen bond. But we'll get there. Let's start with something you've seen 1,000 times and it's never once found strange. You drop an ice cube into a glass of water. What happens? It floats. You've watched this since you were a kid. It's so ordinary, so completely that you never once thought to ask why. You'd never dream of calling it anything but normal. But let me tell you something. If you showed that to a chemist from another planet, a chemist who had spent centuries every other substance in the universe but had never once encountered water, that chemist would faint. They would that is impossible. Solids do not float in their own liquid. Violate everything I know about matter. And that alien chemist would be absolutely right to be shocked. Here's the rule. The rule that virtually everything else in the known universe follows without exception. When a liquid freezes and becomes a solid, it gets denser. The molecules slow down. They lose energy. They pack together more tightly. The solid form is heavier than the liquid form per unit volume. And so the solid sinks. Think about it. Melt iron and pour it into a mold, let it solidify. Solid iron sinks in liquid iron. Freeze alcohol. The solid sinks. Mercury, gold, copper, bismuth, nitrogen, oxygen, sulfur, you name it. Across the entire periodic table, across every substance we have ever studied, the solid sinks in the liquid. That's the rule. One of the most reliable, most universal patterns in all of chemistry. Water looks at that rule and laughs. When water freezes, it expands. It gets about 9% bigger. 9% is not trivial. 9% is enough to burst iron pipes, enough to crack granite boulders, enough to split a sealed glass bottle in your face. Let's learn that last. All the destructive power comes from one simple, outrageous fact. Water, unlike almost everything else in the universe, gets bigger when it gets cold enough to freeze. And because ice is less dense than liquid water, it floats. Now, you might be tempted to file that away as a neat little curiosity and move on. Don't. Because I want to show you what happens to a planet where water behaves like a normal, respectable substance. Imagine a lake in winter. The air above it is dropping, getting colder and colder. The surface of the lake cools first because it's sitting right up against that frigid air. Now, in a normal liquid, what happens? That cold surface layer gets denser than the warmer water below. It sinks. Warmer water from the depths rises up to replace it. That warmer water cools, and it sinks too. Convection. The whole lake gradually, uniformly, mixes and cools from top to bottom. Eventually, the entire lake reaches the freezing point. And then, the first ice crystals form. And because they're denser than the liquid, they sink to the bottom. More ice forms at the surface. It sinks too. The lake freezes from the bottom up, layer by layer, relentlessly. Every fish, every plant, every tadpole, every bacterium, every microscopic creature in that lake, entombed, frozen solid, dead, all of them. And in spring, when the sun returns, the ice at the bottom of the lake is now buried under a layer of water. It's insulated, extraordinarily slow to melt. Some of it might never melt. Year after year, more ice accumulates at the bottom. The shallower regions of the ocean suffer the same fate. Over millions of years, vast quantities of the planet's water get locked away in permanent ice at the bottom of every body of water on Earth. Life in the water. Impossible. And since life first emerged in the water roughly 3.5 billion years ago, no life at all, no fish, no amphibians, no dinosaurs, no mammals, no humans. An empty, frozen, silent world. And it gets worse. Ice is white. It reflects sunlight back into space instead of absorbing it. Dark ocean water warms up when the sun hits it. But if seas started building up permanent ice, eventually that ice would reach the surface. Now you've got vast white sheets reflecting sunlight away. The planet cools further. More ice forms, more reflection, more cooling. A runaway feedback loop. What climatologists call the ice albedo feedback. Without water's density anomaly, Earth might have tipped into a permanent deep freeze early in its history. A snowball planet, white and silent and dead. So this one thing, ice floating, is not a curiosity. It is arguably the single most important physical property of any substance on Earth. And it comes entirely from water's refusal to follow the rules. But here's what's really clever. And I use that word carefully because nature doesn't design things. But sometimes it sure looks like it does. Water does get denser as you cool it, just like any well-behaved liquid, but only down to 4 degrees Celsius. At 4 degrees, water reaches its maximum density. It's at its heaviest. And then something deeply strange kicks in. You cool it further, from 4 degrees down towards zero. And instead of continuing to contract, water starts to expand. It gets lighter. The colder it gets below 4 degrees, the less dense it becomes. Do you see what this does? The coldest water, the water closest to freezing, is lighter than the water below it, so it stays at the surface. It doesn't sink. The dense 4-degree water settles to the bottom and stays there. The lake freezes from the top down. A lid of ice forms on the surface. And that lid, ice is a terrible conductor of heat. Acts like a blanket, an insulating cap. It protects everything beneath it from the killing cold above. The deep water holds at roughly 4 degrees. The fish survive. The plants survive. Life carries on quietly beneath the ice, waiting for spring. All because of one peculiar, rule-breaking property of a molecule you drink every single day without a second thought. If you are not at least a little bit amazed by that, I haven't done my job yet.